Hi class, Dr. Searcy here with the video lecture for Chapter 4 and the odd problems. First, I'll just go over the question for number 1. It says, in words, explain what is measured by sum of squares, variance, and standard deviation. Okay, let's go ahead and tackle one of these, or tackle these one at a time, beginning with that definition of what a sum of squares is. So first, remember, we are often using this abbreviation to refer to sum of squares. The definition of it is that it's the sum of the squared deviations, and then also this is the mathematical expression that we use to express it. Remember that the part in the parentheses, the x minus x bar, is the deviation. And so what we're doing here is we're figuring out all the deviation scores for each x score, and then we're creating a column where we square those values, and then once we've created that value, we sum those scores up. So then the second term, variance, is referred to as the average of the squared deviations. Remember, at least with population, the symbol for this is sigma squared. With the sample, it was lowercase s squared. And at least for the population, the formula was where you're taking the sum of squares and you were dividing by n, right? And that was how we got the variance, or the average of the squared deviations. With the sample, remember that you're basically doing the same thing, except it was the sum of squares divided by the degrees of freedom, which was the sample size minus 1. By the way, the reason why they do that is the theory is that in any sample that you ever collect, you're always going to have one oddball score that you probably should throw out. And so that's what they're doing here. They're saying n minus 1 to get rid of that oddball score. Okay, the third thing that we need to define, though, is standard deviation. You may notice that I'm sometimes going to refer to it as SD, but as far as the symbols, this is now where it was either the lowercase sigma by itself, no longer with the square, and then same thing with the sample version, just the lowercase s. But we were saying that the standard deviation is the standard distance from the mean. With that, you may want to remember that we're talking about a histogram and drawing a curve over the histogram. Remember one thing that I was saying, that in the middle of the curve is going to be your average score. And then below that, we're often going to write our standard deviation units. Just remember that right under the mean, the standard deviation value is 0, right? And the reason why it's 0 is because at that point, we are 0 points or 0 distance away from the mean. And then from there, just remember that we're moving out a standard distance from the mean. And as we move out a standard distance, we count it in terms of units, where that's one standard deviation unit away from the mean. And then as we move out further, we move out by ones, so the next standard deviation unit will be 2. And then so on and so forth. Okay, so the next question is question number 3, and it's saying, describe the scores in a sample that has a standard deviation of 0. Well, what I have written here is that a standard deviation of 0 indicates there is no variability. All scores in the sample have the same value, right? So what that means is, going back to our curve, it's saying that all of the scores are on the mean line. And so because they're all on the mean line, there are no scores that deviate from the mean. And so that's why you have a standard deviation of 0. From there, we have question number 5. And question number 5 is kind of asking a question that I don't think I actually answered. But here the question is saying, calculate the mean and the sum of squares for each of the following samples, right? So you're supposed to do it for this sample and then for that sample. Based on the value for the mean, you should be able to decide which sum of squares formula is better to use. With this part, remember that we said that there were two different kinds of formulas. There was the definitional formula, and there also was the computational formula. And so what they're wanting you to do is figure out which formula would be better to use to calculate the sum of squares for each of these samples. One thing that you may want to note is that had I actually had you do this, you would have had to create an X table for sample A and then do all that stuff that we talked about, right, the other columns, and then do the same exact thing for that sample B, another X column, and then create all those other values. So that's a lot of work. So I didn't go and do it. Instead, what I did was I accidentally did exactly the same thing that I did in the lecture for talking about definitional formulas versus computational formulas. So I'm just going to stick with that. The important thing that I think is happening in this question is that you have a solid understanding of what the definitional formula is, right? Remember, it's the definitional formula in that this is the definition of the sum of squared deviations. There's the deviation, there's the square, there's the sum. And then the other formula was the computational formula, where the sum of squares was calculated by finding the sum of x squared, subtracting it by this division problem, or subtracting this division problem from it, where you had the sum of x in parentheses squared over n. So remember, just the way that we did this was with the definitional formula. We first created a table of the data. Notice I'm not using this data here, I'm just using the data from the lecture. But we said that once we created the table, then we were going to create the sum of x, which was 8 in this case. We were going to note how many people were in the sample, and we were also going to calculate the average of the x values. From there, you're going to use that average score to create that deviation column, where you had this -1, -2, 4, and -1. We already noted how you got those numbers in the video lecture for the textbook. Just remember that then the next step is to take that column of scores and square each value in it so that you could end up with a sum of squares value. In this case, that value was 22. So then remember I said that you could also run the equation using the computational formula, where you would use it in this way instead. If you did do this, the first thing that you would do is create that X table with all the same values. You wouldn't necessarily have to find the mean in this one, because you're not going to really use the mean in this formula. But the next step was to then create the x squared column so that you could know what your sum of x squared was. In this case, it was 38. Once you knew that, then you had all the information that you needed to punch into the formula. Remember that the way the formula was going to work was you had the 38 here, because that was what value here. You put the 8 here, because that's the sum of x. Just make sure that you have to square it. And that's all over 4, which was the sample size. So then the first thing that you did was you did the exponent equation, that was, or the calculation that was where we got the 64. So now it's 38 minus 64 over 4. From there, you calculate the division problem so that you have 38 minus 16. And then from there, you can just go ahead and do the subtraction, which gave you the 22. I'll just note that the reason why the authors were asking this question, right, is because of this point here where they're saying, based on the value for the mean, you should be able to decide which sum of squares formula is better to use. Basically, here's the rule of thumb for that part. I'll just say really quickly. The definitional formula is better, we'll say best, when the mean is a whole number, right? Like a 1, 6, a 0, where it's not a fraction. The reason why that's the case is because if there were a fraction here, then these calculations would get kind of complicated. So that's the situation where you would want to use the computational formula. So we'll say the computational formula is best when the mean is a decimal. The reason why that's the case is because then you could just do these simple calculations to handle the decimal. I will note, though, that for the most part, as we move from chapter to chapter, I will mainly use the computational formula just because it seems to be the most efficient formula of the two. So unless otherwise directed, I most often will use the computational formula. So moving on to the next set of problems, we can say that now we're ready to talk about number 7. On number 7, the question is asking to calculate the sum of squares, the variance, and the standard deviation for the following population. Right here, we want to pay attention to the fact that we are being told that the data that we're looking at is population data as opposed to sample data. You may even notice that they're using population notation. So here are the scores that they're giving us, saying that that's the population data. The other thing that they're saying is that for this, the definitional formula will work the best. So we'll go ahead and follow their advice, and we'll do the equations using the definitional formula. And we're just going to step through it step by step. Remember, the first thing that you're supposed to do is create a table with the data on it. So we've got all of the data inside the table. From there, we calculate the sum of the x values equals 28. We take note of how many participants there were in the study, and then we use those two values to calculate the mean, which is 4. Notice that here, I'm using that lowercase mu to represent the mean, and we're doing that because we're talking about population data. So then from there, the next thing that we're supposed to do is calculate our deviation scores. Again, notice I've tweaked the expression. Before, I've always been writing x minus x bar, but since this is population data, now it's going to be x minus mu. But beyond that, everything's exactly the same. We're still saying, okay, we're saying 8 minus the mean, which is 4, and that's how we got that 4 there. 1 minus 4 is negative 3, and then so on. The important thing that we have to do from here, though, is because we're using the definitional formula, we now have to go and figure out what the squared value is of all of these deviations, right? So this 16 is 4 times 4, 3 times 3 is 9, and so on. From there, though, the important information that we come away with is that our sum of our squared deviations is 28, right? Or that sum of squares is 28. So then we're saying that we've now just calculated that sum of squares value. Remember, the point of doing that is so that we can then use that sum of squares value to calculate variance and standard deviation. First, let's go ahead and remember how we're supposed to calculate variance. Using the population notation, we're saying that the variance formula is lowercase sigma squared equals the sum of squares divided by the capital N. So the numbers that we'd use in this situation is that 28 that we got over here, over that 7 that we get over here, and that gives us a population variance of 4. But then, so we've got that knocked out, we got our variance knocked out, so now we have to take care of that standard deviation. Let's just remember that for the standard deviation, we weren't talking about the population. The symbol that we use for population standard deviation is that lowercase sigma without the exponent. The formula, though, is we're going to calculate the square root of the sum of squares over n. And so the calculation ends up being 28 over 7, or the square root of 28 over 7. That reduces to the square root of 4, which then further reduces to 2. Okay, so now we've also calculated standard deviation as well. And that means that we can move on to the next question, which says, for the following set of scores, right? So for these scores here, if the scores are a population, what are the variance and standard deviation? And then if the scores are a sample, what are the variance and the standard deviation? So now here, they're just making sure that we understand all the symbols that we're supposed to use when the data is population data versus when the data is sample data. One thing that you want to remember is that regardless of whether the data is population or sample, we're going to start off with the same kinds of equations. We're going to start off by taking the data and organizing it in terms of a table. By the way, you may want to notice that the formula that I'm going to use to calculate sum of squares this time is going to be the computational formula. So let's just make note of that. We're using the computational formula. And how did that formula work? Remember, it started off with us creating the table, finding out what our sum of x is, and also finding out what our n is, right? So all the scores added up equals 20. The number of scores that we have is 5. And then we don't need to do this, but I've also gone and calculated the mean of the group. The way that I did that was just simply divided by the 20 by 5. But the next step in the computational formula is then we now create a column of x squared values, right? So 1 times 1 is 1, 4 times 4 is 16, and so on. The reason why we're doing this is because we want to know what the sum of the x squared values are. In this case, we're seeing that the sum is 100. So now we have everything that we need to know to pop everything into our computational sum of squares formula. Remember that the formula is where we are saying that we take the sum of x squared and subtract the division problem that consists of the sum of x in parentheses squared divided by n. So what does that look like in terms of the numbers? That looks like this, right? So we have this 100, that's that sum of x squared, minus 20, that's where we get the 20 from. We got to square the 20, and then it's going to be over 5, because that's where our 5 is. That reduces to 100 minus 400 divided by 5. That further reduces to 100 minus 80, and so we say that our sum of squares value is 20. Notice that we can say that it's 20 regardless of whether we're talking about a population or a sample. It's going to be 20 either way. From there, though, now we have to pay attention to the symbols and whether we're talking about population data or sample data. So for question A, they're saying assume all this is population data. So let's do the equations accordingly. For population variance, this is the formula. Sigma squared equals sum of squares over n. The values that we get for that are that 20 divided by 5 equals 4. We then use that to calculate our population standard deviation, which now is just sigma equals the square root of the sum of squares over n. Again, we're saying 20 over 5 under the square root. That reduces to the square root of 4, which reduces to 2. But then when we go to calculate the sample version of this data, right, for question B, then we're saying that we're using lowercase s to represent the fact that we're talking about sample data. Here, since we're talking about variance, we're going to square that lowercase s, and we're going to say that the formula for it is the sum of squares divided by the degrees of freedom. Now remember, degrees of freedom just simply means that you're taking whatever your n is and you're subtracting 1 from it. So then the formula that we have here is 20 divided by 4, which gives us 5. From there, then we can also calculate the sample standard deviation. The formula for that is now just taking the square root of sum of squares over degrees of freedom. That's going to mean the square root of 20 over 4, which gives us the square root of 5, which then further reduces to 2.24. Okay, so now we can go ahead and move on to our next problem, number 11. Here we're reading, for the following sample of n equals 6 scores, right? Those are the scores there. They first want us to sketch a histogram showing the sample distribution. So that's the histogram that I have here. Remember, these are your x values. These are your y values. X values represent the range of your potential x values, and y always represents frequency, how often each x value has occurred. So then we have the bars representing that. I have this bar at 0 because we had 1 0 in the data, and that's what the height of the bar is reflecting. The bar at 5 is 3 y units big because there are 3 different 5s in the data. And then over here, we had 110 in the data and 111 in the data. And so that's our histogram. Remember that in histogram, when you have bars next to each other, the bars touch each other. From there, question B is saying, locate the value of the sample mean in your sketch and make an estimate of the standard deviation. It's done in the book in example 4.6. So here we're saying, okay, the mean ought to be about 6 on here, right? So I'm just going to put that symbol there, saying that that's the mean, it's 6. From there, what they did in the book was they figured out how far is the closest bar to the mean and how far is the furthest bar to the mean. Here we've got the closest bar being 1 unit away, right? So the mean is 6, the closest bar is 5, so that's 1 bar away. And then we're going to add that to the bar that is the furthest away. That's that 0. Right, so the distance to the 0 is 6. Right, from 6 to 0 is 6. So then we're saying, so we have about a spread of 7. In the book, what they said that they did here was they cut that spread in half to 3.5, and that is now your estimate of where the standard deviation is. Right, so if I wanted to draw like the standard deviation bars, I'd say, okay, here's 6. I'm going to go out this way 3.5 units. That's 1, 2, 3. So we'd say that's where 1 standard deviation bar would go. And then we'd go out in the other direction 2, saying 1, 2, 3.5 units away is where the other one is. So remember what we're doing here is I showed you at the end of the video lecture for chapter 4 is we're creating another row here, and we're calling that our standard deviation units row. On that row, we're saying that wherever the mean is, that's where our 0 standard deviation unit is, right? Because standard deviation is distance away from the mean. Right here, we're right on the mean, so it's not away from the mean, so the distance is 0. From there, though, whereas I've said that, it looks like up to there is the distance of 1 standard deviation unit, and up to here is the distance for the other standard deviation unit. We'd say, okay, so that's where our 1 is for that standard deviation unit, and the 1 for that standard deviation unit is. Remember, the way that we're saying this is, so underneath the curve, within this part, is that 68% of the data. 34% was here, and 34% was there. Okay, so that's all under that 1 standard deviation unit. So there is a question C here. It says, compute the sum of squares, the variance, and the standard deviation for the sample. How well does your estimate compare with the actual value of the sample standard deviation? Well, let's take a look. Let's go ahead and do math here. So first thing that we had to do was, again, I'm using the computational formula to get our sum of squares. You know that I'm doing that because right off the bat, you're seeing our second column is that x squared column. But remember what we had to do was we created our x table. We calculated the sum of x, and we also figured out how many people were in the study. From there, we squared all of our individual x values so that we could get a sum of those individual x values. We found that they were 296. And we're going to use that 296 to calculate now our sum of squares. The way that's going to work is our sum of x squared is going to go there. Remember, here is your sum of x squared. That's what's happening in the parentheses. So that 36 squared over the population, which is, the sample size, which is 6. So from there, first step that we're going to do is we're going to say, what is the answer to that squaring? It gives us 296 minus 1296 over 6. That division problem reduces to 216. So we end up with 296 minus 216, which gives us then this sum of squares value of 80. Okay, but remember what we do is we use that sum of squares value now to go and calculate things like variance, right? So sum of squares over the degrees of freedom. In this case, it's 80 over 5, right? Sum of squares is coming from there. That 5 is coming from 6 being the sample size, but degrees of freedom is n minus 1. So 6 minus 1 is 5. That means that our variance is going to be 16. But from there, we're doing all this to get a sense of what our standard deviation is. Are we right in what we've figured out here? So let's see if that is right. Standard deviation formula, remember, was the square root of the sum of squares divided by degrees of freedom. So we're doing all that, and we say that we end up with a standard deviation of 4. 4 is pretty close to my estimate of 3.5, so I wasn't too far off. Yay! Okay, so let's go ahead and move on to problem number 13. Here we're saying calculate the sum of squares, the variance, and the standard deviation for the following sample, right? So it's a sample of n equals 5 scores, and there's the data. So just to be consistent in how I always do this, I'm saying that I'm again going to use the computational formula. And what I've done is I first created my table of the data. I have added up each of this x values, and I've figured out how many participants I had in the study. Now I'm creating the second column of x squared values so that I can find out what the sum of those x squared values are. Ends up being 216. So now I can use all of my information here to calculate my computational sum of squares equation. Right, so I'm not going to do the generic formula anymore. We're just going to say that now it's 216 minus 30 squared over 5. How am I getting all this? Remember that the 216 is that sum of x squared. The 30 is the sum of x, and the 5 is n. So once we know what our values are, it's time for the math. First thing that we're going to do with the math is we are going to take care of the exponent. That gives us 216 minus 900 divided by 5. From there, the next thing we do is take care of the division problem, which gives us 216 minus 180. And so then we find that our sum of squares value is 36. From there, we're going to use that sum of squares value to calculate our variance. We're using a sample. So the symbol that we're going to use for this is lowercase s squared, and we're going to remember that we have to calculate that degrees of freedom here. So our equation for variance is that sum of squares divided by 4. Why 4? Because it's n minus 1 or 5 minus 1. That gives us a variance of 9. But then they're also asking us to calculate that standard deviation as well. For standard deviation, remember now the symbol is the lowercase s, and the formula is the square root of sum of squares divided by degrees of freedom. And we'll just note that the previous equation is now just being placed under the square root. So we have to now find the square root of that 9, which gives us 3. So for this problem, whereas the variance was 9, the standard deviation is 3. Okay, let's go ahead and move on to the next problem here. Actually, I want to do something. I just want to make sure you understand what this 3 means then. Right, so I'm just going to draw a quick curve here. And remember what we've been saying here is we can have our x values under the curve, and below that we can have our mean, and we're always saying that the mean, whatever the mean is going to be this value right in the middle. Right, so in this case, we know that our mean is 30, so the mean is going to be 30. But the other thing that I want you to remember is that we're also tracking this standard deviation. Well, in this case, it's a lowercase s. So remember that you're always going to have your standard deviation being 0 right under the mean. And then you're saying that you're going to go out and you're going to have these standard deviation units. They're going to be away from the mean. Basically, what we're saying with this 3 is that to go out to the 1 in terms of the standard deviation units, we're going out 3 spaces on the number line, right? So we've got 30, 31, 32, 33. So it's saying that on your right side of the number line, 1 standard deviation unit away from the mean is 3 x values away. Why is it the 3? Because that's what we have here. Same thing with the other side of your curve. 30 is the mean. Moving 3 digits away, we go 29, 28, 27. So on this side, 27 is 1 standard deviation unit away from the mean. Why is it the 3? Because that's the value that we've just calculated there. Okay, let's go ahead and go on to our number 15. And here, what we have to account for is when changes have been made to the data again, right? So the question is reading, after 6 points have been added to every score in a sample, the mean, so let's just note that the operation that we're talking about here is addition, right? Every score has been added, or 6 points have been added to every score. So after you've done this, you say that you get this mean of 70, and the standard deviation is 13. What were the values for the mean and the standard deviation for the original sample? Well, to answer that question, we need to know what we would do to get back to the original. And that is said here. So it says, to get the original sample mean, we're going to take that mean that we got, this is the new mean, that's 70, and we're just going to simply undo what we had done before. We're going to subtract those 6 points that we'd added. And when we do that, we see that, oh, okay, 64 then was the original mean. However, we also have to see what we do to the standard deviation. It turns out adding new scores does not change the standard deviation. So what this is saying is that we're not going to do anything to change the standard deviation because we don't need to. So, in answer to the question, what were the values for the mean and the standard deviation for the original sample? Our original sample average was 64. How do we get that 64? We just simply undid what we did before. We took that 6 points that we had added and we subtracted them from the new mean, and that gave us the 64. But because adding new scores does not change S is still the same as it was before, right? So it's the same as it was originally. Okay, but then there's question B, which reads, after every score in a sample is multiplied, right? So now they're saying multiplication by 3. The mean is found to be 48, and the standard deviation is 18. What were the values for the mean and the standard deviation for the original sample? Okay, so here they're saying, now what we're going to do is we're going to find out what the original numbers were. And here's the logic that's going to lay it out. Since we multiplied by 3, right? We multiplied both the original sample mean and the original standard deviation. We multiplied both by 3. We're going to divide both by 3. We're going to divide the new standard deviation, the new average and the new standard deviation by 3. So what that means is we end up with this. We end up with, whereas the new mean was 48 and the new standard deviation was 18, when we go and undo what we had done by dividing by 3, we find that the original mean was 16 and the original standard deviation was 6. Okay, so let's go ahead and move on to the next question from here. And I just want to note that we're going to read it this way. It says, kind of using the logic that we used up here, question 17 is following on from question 15. They're saying that we had an original sample of data. That original sample was containing those numbers. But we didn't like the fact that we had fractions in there. It makes it kind of hard to deal with the data when you got fractions. So we simplified the arithmetic by first multiplying each score by 2 to obtain a new sample. Right? We didn't like the fact that we had the fractions in there, so we just multiplied everything by 2, and it gave us these whole numbers. So now they want us to compute the mean and the standard deviation for the new sample when we do this. Okay, so we're getting at the mean and we're getting the new standard deviation. That means that we have to do a sum of squares equation all over again. Again, I'm going to start off by using a computational formula to do it. Right, and you're seeing this computational because I'm calculating a x squared value. First thing that we're going to do is we're going to take all of our data, we're going to stack it in a table, we're going to find out what the sum is, then we're going to find out what the sample size is. I did include the mean here, but I didn't need to. And the next important thing that we have to do is just square each x value, right? So 0 times 0 is 0, 2 times 2 is 4, and so on. The important thing is that we then find that the sum of x squared is 46. So now we have the 3 numbers that we need for our computational sum of squares equation. And it's going to look like this. Right, so we're calculating sum of squares now. The way that we're going to do it is we're taking our 46, popping it in there. We're taking our 12, and we're popping it in here. Notice I've written it this way, 12 times 12 instead of with the exponent. And we have the 8 representing the sample size. So first thing I did was I calculated the exponent formula. That gave us 12 times 12 is 144. Now I have to just solve the division problem. That gives us 46 minus 18, which then gives us a sum of squares value of 28. Now we'll use that sum of squares value to figure out the sample variance. Remember that the formula is the sum of squares over the degrees of freedom, which gives us that 28 over 7. Why 7? Because degrees of freedom is n minus 1, or 8 minus 1. That then tells us that our variance is 4. Okay, so then that's everything that we needed to do for question A, right? We found out what our mean was. That was what they were asking for right there. And we also found out what our standard deviation was. That was this here. I don't think I did that. Okay. Standard deviation follows from variance. Standard deviation is where you take the square root of the variance. Our variance was 4, and so what's the square root of 4? It is 2. Okay, so that leaves us now to move on to question B, which is using the values obtained in part A, what are the values for the mean and the standard deviation for the original sample? Well, here we've got an answer to that. Since we multiplied by 2, right, and based on what we said here in question B, to find the original sample mean and the original sample standard deviation, then we're going to divide by 2, right, using the same logic that we talked about right here. So when we do that, we find that our original sample average was that 1.5 divided by 2, which gives us 0.75. Oh, that's why I calculated the mean there. And also, our original standard deviation was 2 divided by 2. Why am I using 2 right here? Because that's what our standard deviation is here. We're going to divide it by 2, and so that means that the original standard deviation was 1. Okay. So now we're going to move on to question 19. And we are saying that the question here is now the range is completely determined by the two extreme scores in the distribution, right? We already said that. Remember, the range is your largest score minus your smallest score. The standard deviation, on the other hand, uses every score. So first thing that they want us to do is compute the range. In the book, they talk about different ways that we can compute the range. I'm just saying largest score minus smallest score. And then they also want us to calculate the standard deviation for the following sample of n equals 5 scores. Note that there are 3 scores clustered around the mean in the center of the distribution and 2 extreme values, right? So what they mean is, looks like the mean is this 7, and you got a score of 6 near it, and you got a score of 8 near it. That's what they mean with this part here. Scores are clustered around the mean in the center of the distribution. Oh, and then this 14 and this 0 are your 2 extreme values. So, compute the range and standard deviation. Let's see if I got those here. Oh yeah, so first off, we're talking about question A. The range there is 14 minus 0, which gives you a range of 14. From there, I'm going to use the computational formula to calculate standard deviation for this set of data. And that is going to be where we've got our table. The sum is 35. We had 5 participants. The average is 7. Didn't need the average, but I calculated it anyway. Next thing that we need to do is calculate that column of x squared values. So you're seeing how each value here is the square of the original x's. The sum of those x squared values is 345, right? So now we have the 3 numbers that we need to use to calculate our sum of squares equation. It's going to look like this. 345 minus 35 squared over 5. So first thing that we're going to do is take care of that squared value. It ends up being 1,225 over 5. We're going to take care of the division problem. That gives us 345 minus 245. So then we end up with a sum of squares value of 100. Okay, so then we have to keep on moving because we're moving towards that standard deviation. So when I got standard deviation, I just said I'm taking the sum of squares, which is 100, and dividing it by degrees of freedom, which is 4. Why is it 4? Because remember, degrees of freedom is n minus 1, so 5 minus 1 gives us 4. So then the solution to that problem is we have the square root of 25, which is 5. All right, so in this problem, the standard deviation is 5. That's everything that we needed to do for A. But now there's a whole other part to this, a B problem. Now what they're saying is that they're going to give us a new set of data, and the thing that they want us to notice is that they broke up the cluster in the center of the distribution by moving 2 of the central scores out to the extreme, right? So we said the 7 was in the middle. Before you had a 6 and an 8 right by that 7. Now those 2 numbers are on the extreme, over in the 0 and over in the 14. Once again, compute range and standard deviation. Okay, so now that's going to be, we're now calculating for B. First thing, I don't think I calculated the range to start with. Let's just note that the range is exactly the same, right? So for B, again, it's 14 minus 0 equals 14, and that's the range. So that's exactly the same. But what we're going to see is that the standard deviation should be different since we have a different spread here. Let's see if that will be the case. So we start out by creating our table. I'm going to do the computational formula again, and you're seeing that because I've got my x squared value there. One thing that's interesting is that you're seeing that the sum is still the same, the number of participants is still the same, and the average is still the same. But once we start to move over to our x squared values, we're seeing that looks like our sum of squares is going to be different, right? Because before it was 345, now it's 441. So we're going to use our sum of squares value to calculate our, we're going to use our sum of x squared values to calculate now our sum of squares. Remember, we need this 441, we need that 35, and we need that 5. The way it's all going to work is 441 is going to go here, 35 is going to go there, and then the 5 is going to go there. Okay, so what we end up with is a sum of squares value of 196. Already, you're seeing something that's kind of interesting. Whereas in question A, when the data was clustered around the mean, the sum of squares was 100. Now in question B, where the data is clustered on the ends or the extremes, your sum of squares is 196. Let's see how that affects the standard deviation. So we're taking the standard deviation, we're saying it's going to be 196 divided by 4, and then we're going to take the square root of that. We end up with a standard deviation of 7. So what we're supposed to do now is compare the standard deviation for when the data were clustered around the mean and compare them to when the data were spread out to the extremes. What we're seeing happens is when the data is spread out, the standard deviation is bigger. When the data is closer to the mean, the standard deviation is smaller. So, okay, so we got question C. Looks like I started to answer question C, but I didn't finish. So let's see if I can do it off the top of my head here. According to the range, how do the two distributions compare in variability? Well, according to the range, the two distributions are, we'll say they are the same. Why am I saying that they're the same? Because when we calculated range, we got a range of 14 in both samples. But with regard to standard deviation, thing that we can say is that the sample with extreme scores had a larger standard deviation. I'm just going to use S as the symbol for that, right? Sample standard deviation. Okay, so now this allows us to move on to our next problem, number 21. And I've taken a huge amount of work and kind of cheated to make it just a small amount of work. I'll show you how. The question reads, within a population, right? So I guess that's the first thing that we need to know is that we're working with a population, and I already see that I screwed up. But we'll get to that. The differences that exist from one person to another person are often called diversity. Yeah, another name for variability. Researchers comparing cognitive skills for younger adults and older adults typically find greater differences, greater diversity in the older population. I don't like the fact they've switched. The whole name of this chapter is variability. And that's what they mean here by using these terms, diversity. So anyway, they're saying you should find more variability here and less variability here. More variability with older folks and less variability with younger folks. Right, that's here what they just said. Typically find greater differences, greater diversity in the older population. So, then they say, following are typical data showing problem-solving scores for the two groups of participants. Right, so you got the older individuals and you got the younger individuals. These are the scores for the older folks. These are the scores for the younger folks. The thing that they ask us to do is to compute the mean, the variance, and the standard deviation for each group. This is where I'm saying that I skipped that. That's a lot of work. We're on problem number 21. I don't feel like doing all that work all over again. And we've just done that several times. So what I've done is I skipped over that to now just talk about this problem, this part B of the problem. Is one group of scores noticeably more variable, more diverse than the other. So I have the scores that they wanted us to calculate here. Although I will note that when I wrote this out, I wasn't paying attention to the fact that they said that this was a population and not sample. So I'm going to go and correct that now. I am using incorrect terms here, right? These are all sample terms. Instead of X bar, what I should have written down here is mu. Mu for population mean as opposed to sample mean. Instead of having this lowercase s squared here, what I should have there is lowercase sigma squared. Then same thing down here. So that's variance, remember. Down here is standard deviation. And the symbol for population standard deviation is lowercase sigma. You may also notice that for the sum of squares, it doesn't matter. Sum of squares is the same symbol regardless of whether you're talking about population or sample. So let me just draw some equal signs here. And now we can do this comparison of the data. First off, the thing that we want to see is that with regard to the mean, there was a smaller mean for the older folks than there was for the younger folks, which is interesting. But then from there, now we're starting to talk about variability with these other numbers, right? And variability, how far is a score from like the rest of the scores or from the mean of the distribution. Here we're seeing right off the bat that the olders have a larger degree of variability than do the youngers. And I think that you can see that in the spread of the data, right? So if you look at the youngers, it seems like whereas their mean is 7, you have a lot of numbers that are close to the 7. Right, you have that 9, that's close to 7. 6 is close to 8, is close to 7. 6 is even close to 7. And so you have less variability here. That less variability is being reflected in this sum of squares value. Notice over here, though, right? So for the older folks, the mean was 5.47. You have numbers here that are far away from the 5.47. Like you got that 9, you got this 2. Those are spread out from the mean, and so that's why you have a large degree of sum of squares. And then notice how that large degree of variability. So we'll just say, okay, you got more variability here and less variability there. Notice how that then gets reflected in your variance and your standard deviation. For variance, we have a larger number here and a smaller number there. Same thing with standard deviation, a larger standard deviation and a smaller standard deviation. You know, I do want to point out what this means and what that means in terms of the curves, right? So let's just note again, how do we read standard deviation when we look at the histograms? First, remember that what we're saying is we've got some histogram and we have put a curve over that histogram, and it's a normal curve. And in the middle of the normal curve, we say that we've got our mean. Okay, spell that correctly, our mean. So in the lecture on the textbook, I noted that what we're going to start doing here is we're going to create these rows of information under the curve. Whereas maybe the first row could be the number of x values. That's the numbers that's going to go on the tick mark line. But below that, we're going to account for another row that's going to represent the mean. In this case, it's population data, so I have to write it as a mu. Okay, so, and remember, when we look at it in terms of a row for the mu, remember that the mean is always going to be some value in the middle. In this case, the mean is going to be that 5.47 for the group. And then after that, we also always are going to be accounting for that standard deviation. That's going to be like this third row that we're going to have down here. And so just remember that the way that the standard deviation is going to work is it's going to be some zero value right under the mean. Why? Because standard deviation is the standard distance away from the mean. If you are right here, you're not away from the mean, so the standard distance is 0. But then we're saying we're going to move out one standard deviation unit away from the tick at a time, or away from the mean at a time. Right? So that would be like one standard deviation unit there, one standard deviation unit there. Thing that you want to remember is what that 2.17 is. It's saying that that one standard deviation unit is 2.17 ticks away from the mean, right? So for this, that one standard deviation unit would be whatever 5.47 is plus 2.17. Let's see, so it's 14.56. So if we move away from the mean and we move one standard deviation unit away, on that original x bar, it's to 7.66. On this side, it's going to be 5.47 minus that 2.17, right? Because now we're moving this way. So it's 0, 3. So it's going to be, for this standard deviation unit, it's going to be that 3.3 on the number line. Okay, so our mean is 5.47. One standard deviation unit away from the 5.47 is 7.66 in the positive direction. 1 standard deviation unit away in the negative direction is 3.3. How did we get that? We got that because we said standard deviation is 2.17. Okay, so the logic would hold here too, but I don't want to waste your time by creating a whole nother graph. Let's just go ahead and move on to the next problem now. And I think it's going to further explain this idea. So number 23 says, a population has a mean of 50 and a standard deviation of 20. Would a score of x equals 70 be considered an extreme value out in the tail in this sample? Okay, so to answer this question, let's just kind of see what we would do in terms of drawing it. Here's a histogram that I've just drawn, and we've got the curve that's going to go over the histogram. I didn't do the 3 rows. Instead, I just did the 2 rows. I did a mean row and a standard deviation unit row. But you could say that there's the x row above it, right? And that x row is going to be here. Okay, so here we're saying that our mean is 50, right? The line in the middle is always your mean. And so if that's the case, the number that's going to go into that line is 50. Mean is in the middle, mean equals 50, so 50 is the middle. Then we're saying, and a standard deviation of 20. Okay, so what that means is, when we write standard deviation, it's 0 right under the 50. We move out 1 standard deviation unit away from the 50. In this case, it's 20. So what we're going to do is we're going to move out 20 spaces and say that's where our 1 standard deviation unit is. What is 20 spaces away from 50? That's 70. Same thing moving away from the mean in the negative direction. We're moving out 1 standard deviation unit away from the mean. In terms of x values, that's 20 x values away, so 50 minus 20 means that 1 standard deviation unit is 30, is x value of 30. Okay, so now the question that they're asking with this is, if I have an x value of 70, right? So just say, okay, I got an x and it's right there. The question that they're asking is that 70 an extreme value? Here is our answer to that question. 70 is 1 standard deviation unit away from the mean. Therefore, it is not extreme. I'll just give you a sense. A value that would be extreme is a value that's in the what we call the tail of the curve, right? This small chunk here or this small chunk over here. In this case, for this problem, the 70 is like right here. So for that reason, it's not extreme. But let's take a look at question B. Here it's saying, if the standard deviation were 5, would a x value of 70 be considered an extreme value? Well, so here now we've got a different curve that we're talking about. This time we're still saying that the mu is in the middle, right? The mean is in the middle, and we're still even saying that that mean is 50. But now they're saying a standard deviation unit is 5 x values away from the mean. So that means when we go to draw in our standard deviation row here, right, whereas our standard deviation units start out at 0 under the mean, we move away from the mean in terms of our standard deviation units away. We're going to move 5 x values away at a time, right, because our standard deviation is 5. So 1 unit away would be 50 to 55. A second unit away would be 55 to 60. The third would be 60 to 65. And then the fourth would be 65 to 70. So now what we're saying is that, yeah, now that 70 is in the extreme, it's not 1 standard deviation unit away, it is 4 standard deviation units away. So, because 70 is 4 standard deviation units away from the mean, it is an extreme score. All right, that is all of the problems. Thank you very much. I'll see you next week.